Well, thank you all for coming. It's much appreciated. Thank you so much, Paul, as well. So yeah, in my short talk, I just wanted to sort of talk about the three things. So the sort of theory. So how did we get to where we are? The reality, so how an organization can actually implement some of this Gen AI stuff, and what a future might hold as well. But before I wanted to start, I just wanted to have a quick slide about myself. So as Paul mentioned, I have a PhD in statistics. I joined NICD 2 years ago. I work as a data scientist, specializing in all things statistics and machine learning related. I'm particularly interested in two things, which is AI assurance and large language models. And I wanted to apologize just for my picture as well. As you can see, I've aged quite a lot. So I decided to perhaps use some of those Gen AI models to actually update my profile picture, as I didn't have enough cash to obviously fund another photographer. So here's just a few attempts. So the very first one is me looking like a cool-looking anime character, which works okay. The second one is me as a Mona Lisa, which I don't think it even looks like me. I think it looks more like my colleague Peter over there. And then finally, there's me as a cute-looking teddy bear, and I think this is going to be my new profile picture going forwards. So yeah, as I sort of mentioned, I'm a data scientist, but I fully anticipate to become a prompt engineer in the future. And I will talk about it in more detail later on. So I wanted to talk about the theory. So I think there's a lot of misconceptions. There's lots of misunderstanding as to what certain things are and what certain things are not. So I wanted to sort of clarify a few definitions, and then essentially talk about some of the key breakthroughs that allowed us to get to where we are. So first of all, I thought that it would be useful to sort of define a few key terms, such as AI, machine learning, and deep learning. I felt compelled to do so because I think a lot of these terms are used sort of interchangeably, whereas they sort of mean slightly different things. So I felt like it would be useful to I'm a visual person, so I thought that it would be useful to perhaps sort of see the hierarchy of these terms. And obviously, if you want to look at hierarchies, I think the best way to visualize it is with a babushka doll or a Russian doll. So as you can see, we get AI, which is essentially a field, and then it has a variety of different subfields. So in terms of AI, I mean, a lot of people would say that it's a reasonably new field. One of the sort of very first definitions is by this guy called John McCarthy, one of the fathers of AI. And it defines AI as the science and engineering of making intelligent machines. And I think that's quite a good definition, but it is rather circular, because obviously it has intelligence in it. So I thought, okay, maybe perhaps I can look at some other definitions. So the next one, I thought, maybe let's check out our friends at the European Commission. So they actually have a quite long, convoluted definition of AI, which is, I'm not even going to repeat it. I think it has too many words. I think it has a lot of terms which are sort of conflated, like prediction and recommendation. And it sort of focuses too much on, things which are to do with those matters, predictions and stuff. So then I thought maybe Google will do a better job. But again, I think this definition focuses too much on the sort of data side of things. So the best definition I managed to find is by Stuart Russell. So Stuart Russell defines AI rather cleanly as anything to do with building machines that do the right thing, that act in ways that can be expected to achieve their objectives. And I think this is quite a broad definition which captures a variety of different things like learning systems and robotics. So I think this is a quite clean definition of AI. The next thing to do would be to define machine learning. And I don't think it gets any better than a definition by Tom Mitchell. He says the machine learning has to have three key components. First of all, you need to have a task. Then you need to have some sort of experience. And then you need to have a performance measure. And essentially, the aim of the game is to get better at your task with some sort of experience that you have as measured by P. And this definition is very broad, and it actually captures a variety of different things. So under that definition, an autonomous vehicle could be a type of machine learning problem. Here, for example, a task could be something like driving on a motorway. Training would be your sequence of images and steering commands. And then performance measure would be the average distance before you have an error or a crash. Another one would be something that maybe perhaps other people are more familiar with, which is sort of data analytics, text. So for example, another task could be something like sentiment analysis of social media, Twitter posts. Training would be, your data set of social media posts together with the labels. And then the performance measure would be something like accuracy of actually classifying your sentiment. So that's essentially machine learning definition. I think it's quite a good one. Thank you, Tom Mitchell. Now, when it came to writing these slides, I got a little bit tired. So obviously, as it is very cliched, I enlisted the help of ChatGPT to help me with the definition of deep learning. It did a reasonable job. It defined it as a subfield of machine learning, which is good. But I don't think it was as clean as a definition of Yann LeCun, one of the fathers of deep learning. So he defines deep learning as anything to do with constructing neural networks, which are considered to be mathematical approximations of a brain, and training them using gradient-based optimization. So I think that's essentially as clean as it gets. It's a type of machine learning where we use neural networks. Now I just wanted to have a very quick diversion. So I wanted to talk about two different types of models that we typically encounter in machine learning and deep learning. So typically, we can actually classify our models as either discriminative or generative. So a discriminative model typically just learns the decision boundary. So it just approximates the conditional probability y given x. So it learns the sort of mapping between your inputs and labels. So you can't really do anything like generating data from that type of a model. And discriminative models are models which have been very popular over the last few decades. When you think about logistic regression, when you think about random forest classifiers, that sort of stuff, that all falls under that sort of type of discriminative model. A generative model does things slightly differently. Rather than just learning the decision boundary, it tries to learn the probability distributions of the underlying data. So by doing so, you get a slightly richer representation. Now, I think generative models are pretty cool, and obviously they've been getting more and more prominence, but that concept has been around for quite some time. And I think generative models are slightly different to Gen AI, and this is essentially my next slide. So in my view, not all generative models are Gen AI. In order for a model to be a Gen AI, you need to generate new content, which is in an unstructured way. So it needs to be content which is unstructured data. So Gen AI is a generative model which generates either a natural or a programming language, an image, a video, or an audio. So if your generative model outputs a number, a label, or probability, and that's it, to me, that's not Gen AI, and Google seems to agree with that. So I think that's essentially as far as it goes with our definitions. However, it's also important to cover a very important concept, which is foundation models. So foundation models is a term that has been sort of, I think, first coined by Stanford University in 2021. And it actually describes a broader paradigm shift in the AI research. So previously, the focus was on developing task-specific models, which have been trained on narrow data. So the focus previously was on training, say, a hot dog classifier or a banana classifier. Now, the focus for us is to develop multi-purpose models, which are trained on broad data. And as you can see from that figure, that broad data could be code, images, text, et cetera, and the aim of the game is to get a model which sort of captures a broader understanding of the world and then perhaps adapt it later on for a specific task. And then, obviously, a lot of people have been talking about large language models. And those models, to me, are a subset of foundation models that deal with just text. So they generate text, and they address text-specific tasks. So those tasks could be something like sentiment analysis. It could be something like named entity recognition, et cetera, et cetera. So not all foundation models have to be Gen AI. So they don't necessarily have to be generative in nature. So a good example of that would be a BERT. BERT is a transformer model created in 2018. It's a foundation model because it can essentially deal with a variety of different natural language processing tasks, but it can't generate new content. So not all Gen AI are foundation models and vice versa. So in terms of Gen AI, I think it all sort of kicked off in 2014 with the variational autoencoder, which was a very important model. Recently, the focus has been on developing models which are either transformer-based or stable diffusion-based, or merging them together to create a multimodal models. So, yeah, the vast majority of these models will be of those two forms. And the reason why Gen AI has been so successful and captured the attention of so many people, I think, is due to three key breakthroughs. So the very first breakthrough is self-supervised learning, and it is a concept that goes back to the sort of 1980s with the denoising autoencoder. It was kind of revived by Yoshua Bengio in 2008, and then it really took off with the BERT paper in 2018. So here, the idea is that we can actually use input and input only to actually train the system. So with supervised learning, we typically need to have labels, and we need to have a set of inputs. With reinforcement learning, we need to have a reward or something like this. With self-supervised learning, all we need is essentially an input. And the idea is that we either reconstruct the input or we predict the missing parts of the input. So if you want to do causal language modeling, which is essentially how GPT-based models are trained, all you have to do is leave the last word out and try to predict it. So that's called causal language modeling. And you can also do mask language modeling if you want to train a BERT-type model, where you essentially just try to predict the random word from your training corpus. And that's illustrated by this figure as well. So we essentially get input, we get some text, we mask out some words, and we try to predict it. The reason why that's such a successful technique is because it reduces the need for a human annotator, so we no longer require labels. And also by, for example, in the case of text, in order to predict the missing word, we need to actually acquire the understanding of the language. So that was the very first key breakthrough which really kicked off this sort of Gen AI field. The second breakthrough was actually finding the promising architectures. So in our case, we're talking about text. Transformers really have taken off. The reason why transformers are so successful is because of three things. They have this attention mechanism, which actually captures context between words. They're able to process sequences of words very well with positional encodings, and you can actually parallelize them very well. So that means that you can train them much more faster than, for example, recurrent neural networks. So if you do self-supervised learning with the right architecture, you can essentially scale up very well. And then the third sort of big breakthrough was a paper from 2020 by Kaplan, who said that if you scale up three things, which is compute, data, and model size, for transformer-based architectures, you get huge improvements in performance. And essentially, over the next sort of 3 years, that's what people have been doing. They've been scaling up model size. As you can see, we've now have models which are in the sort of trillions of parameters with things like GPT-4. We've also scaled up data sets. So we've gone from 3 billion tokens for BERT to 1.4 trillion tokens for chinchilla. And as you can see, the names of these models are getting more and more weird. Yeah, I don't even know what chinchilla is. I think there's also alpaca these days. Yeah, it's pretty crazy stuff. So those three things, those three key breakthroughs have actually created something very interesting, actually. So we've noticed that with really large models, we get these emergent abilities. So we actually get some sort of abilities which are not really observed for smaller models. So one of my favorite example of emergence, because these three are rather dull, we're talking about arithmetic, adding up, I think, two-digit numbers. We're talking about middle, high school exams and word and context. My favorite example of emergence, after you see this wonderful GIF, is emoji movie. So it turns out that some large language models are now able to work out a movie title from an emoji sequence, which shows that they can do popular culture and they have contextual understanding of emojis. So it's actually very interesting. So I haven't seen Finding Nemo, and I've had many arguments with my girlfriend as to whether that sequence of emojis is actually the correct one, because she believed it should be just magnifying glass and one fish. But apparently, so actually on the GitHub for this emoji test, they actually have the justification as to why they have 3 fishes and 1 human. Apparently, it fits the plot better. So I'm going to trust them on that. So obviously, we have very powerful large language models. They do a lot of wonderful things. They are state-of-the-art for a variety of different tasks, like guessing emojis, etc., etc. But that doesn't necessarily make them very good assistants. So as you can see, here's just a screenshot of a completion to a prompt by GPT-3 model. And it doesn't do a very good job. It just gives you frequent words, but it doesn't necessarily adhere to the sort of instruction, which is to explain the moon landing to a 6-year-old. So in addition to being good at a variety of different tasks in order to be a good assistant, these models need to essentially follow instructions. They need to perform complex reasoning tasks, and they need to generalize to unseen instructions. And this is what the sort of latest research have been doing. So it turns out that if you grab a large language model, and if you actually fine-tune it on tasks which are phrased as instructions, that enables the model to then follow instructions much better. It also improves its performance for zero-shot learning tasks, where we don't necessarily have any examples. So that research was very hot in about 2021, 2022. It also turned out that if you include not just natural language data in your training set, if you include some code, you actually get a much better performance on complex reasoning tasks. So these days, the vast majority of these models will be trained with a considerable percentage of code in addition to natural language processing. The idea here is that if you, for example, learn how to do object-oriented programming, you're able to break down a complex problem into smaller subsets of subtasks. People got quite excited about tree of thought prompting as well, so including intermediate steps towards solving the problem. That seems to also sort of nudge the language model into doing things which require complex reasoning. And then also in-context learning is a thing. So if you give an example within your prompt of what is your input and what is your output, it seems to help with dealing with potentially unobserved tasks that can be solved with few-shot learning. So here, ChatGPT learns a mapping between rap songs being egg and then grunge songs being banana. So that's pretty cool. I wanted to use excellent and bad, but unfortunately I was overwritten. So obviously some of that reinforcement learning and human feedback disallows me from performing certain tasks. But yeah, that's essentially how we've gotten from a very capable large language models to actually language models which are assistants. So we need to train on code, we need to do instruction fine-tuning, we potentially need some reinforcement learning in there as well. But that's how we can go from something that's just a large language model, something that just completes text, to something that can actually follow instructions. So the next sort of section of my slides is about the sort of reality and the business side of things. I like talking about business, so I thought that would be quite good. So obviously, so far, my talk has been quite researchy, so I thought, let's talk about the sort of applications that leverage some of these techniques. So as you can see, the application landscape is growing. I think there is obviously plenty of applications which are founded upon the text large language models. So we have obviously Microsoft suite of tools, email autocompletion. We have the same about GitHub Copilot with code. My favorite application, unfortunately, is no longer available. It allowed me to create a Drake song from any text. So it was an example of a text to audio model. But obviously, that had some sort of copyright problems, so obviously that no longer exists. But the application is definitely, the application landscape is certainly growing, which is great. And actually, McKinsey, one of the big consultancies, believed that there is an entire value chain which sort of emerged very quickly. And for anyone that would like to enter this market, obviously entering at the sort of bottom level of hardware level, it's probably going to be tricky. It will be very tricky to compete against NVIDIA or a Taiwanese semiconductor chip company. But there's definitely quite a lot of opportunity to develop applications or develop services around that technology. Obviously, for me, I think that would be great. I think there will be plenty of money in upskilling for Gen AI, so I'm very excited. And in terms of how most people could leverage Gen AI in your organizations, I think there are typically 5 key technical pathways to do so. Some of them are more accessible than the others. So typically, you could obviously try to train your model from scratch, but unless you have access to billions and billions of pounds, that's probably not the best option. The second option would be to perhaps adapt an open source model in-house. And then I think the next points, so 3 to 5, are sort of the most plausible for most. It's to either build software layers in an open source model API or a closed source model API, or use software as a service tool, so something like a Copilot. I think it's important to ensure that we know what are the repercussions of using closed source models. So obviously, typically, you don't want to give up too much of your data to a data center in California. So I would definitely encourage businesses to sort of focus on points 2 and 3 and use open source where possible. I think it's also important to use this stuff responsibly. So I think there are obviously a variety of different dimensions. One of them is trustworthiness. So is the model fair? Is the model secure? That sort of stuff is quite important. There's obviously a lot of legal repercussions of using this stuff. In terms of intellectual property, I think this field is definitely something that's a bit of a minefield. In terms of regulation, we're still at very early stages. People don't really know what to do in terms of regulation. Another important thing is to consider the impact of some of these technology on the workers. So in my view, I think the focus should be on augmentation of the worker with these tools rather than automating the worker. And some people are also concerned about the environmental impact of these technologies. So that needs to be factored into any sort of business strategy. And then I just wanted to conclude by thinking about the future and what could be the next steps. So at the minute, there is a lot of research which goes into leveraging large language models to use tools. So to use things like Google, use things like Wolfram Alpha. That seems to definitely decrease the amount of hallucination that these models do. But also some people think that that could be the new way of interacting with the internet. So rather than, for example, booking my own flights, which I don't do, thankfully I have my girlfriend to do it for me, there is a possibility that we'll be able to use and interact with a large language model to do tasks like this. Another thing that people are quite excited is actually incorporating more knowledge into these models, so actually making them more multimodal. So the minute they typically leverage text and maybe perhaps image data. And there are now attempts to create models which actually learn from more, so like 3D sensors, video, audio, because that's meant to replicate how humans learn. So we don't just learn from text, we learn from physical experience, we learn about the world with interacting with the world. And I think another thing that's very important to consider is how do you actually prevent from creation of monopolies. At the minute, OpenAI is probably one of the biggest players that would like to definitely position themselves as a sort of number one. Do we think that's the best thing? Probably not. Do we need to support open source community as much as we can? Probably yes. So yeah, there's lots of things happening, there's lots of moving parts. Things are obviously shifting at a very rapid pace, so it's very difficult to speculate where the future goes. But I definitely think we need to consider some of these things. And as I sort of mentioned in the sort of previous slide about using these technologies responsibly, we need to think about the sort of regulatory side of things as well. And I think that's me. So thank you so much for your attention. It's much appreciated.